Morning, everyone. So in this chapter, we've been looking at chemical equilibrium. We've been looking at reactions that not only are reversible, they can go in the forward direction or the reverse direction. Whether you start off with reactants or products, some equations will end up hitting something called equilibrium. Equilibrium is this notion, macroscopically things don't change anymore, but microscopically the reactions are occurring. How do we keep those two things together is because they change at exactly the same rate, so forward rate equals reverse rate. When we were at equilibrium, we started looking at a guy called Le Chatelier, and basically it says you can poke at the system, you can try to change the temperature, try to change the pressure, and basically things are going to happen in the system that are going to try to work against what we do. So I try to heat it up, the system's going to try to cool it down. If I try to make it colder, the system's going to try to heat it up. So nature just tries to undo what we do. In yesterday's lesson, we started looking at the little bit of the math here. We introduced what was referred to as the equilibrium constant. It's a number that describes the relative amounts inside an equilibrium system. Today, we're going to start taking a look at the math in a little more detail and what's referred to as an ice table. So let's begin with a warm-up question here, just practicing some of those KEQ expressions here. So let's say I was given the following. I'm going to have benzene, which is C6H6. This one here is a liquid. It's going to react with bromine. This is an equilibrium here, C6H5, Br, also a liquid, and then we have HBr as a gas. So that's one expression. I'm going to give you one more here. Let's do H2 as a gas and half O2 as a gas. Right? It's strange that they have a fraction there, but let's see what ends up happening here. And this ends up producing water as a liquid. Right? All I want you to do in these expressions here is state the equilibrium constant expression, state the KEQ expression. So even before we put numbers in today's lesson here, see if you could do a product over reactant. Pretty much, if you remember from yesterday's lesson here, KEQ was this ratio, products over reactants, so that's unchanged. The bigger the number, the more products are going to be. We had two little notes here in the fact KEQ we always ignores any solids because those have constant composition. You may have more or less solid, but when you work with the ratio like a density, it actually cancels out. Ignores solids and pure liquids. And pure liquids are the things that are the only L in the entire equation. So I chose an equation for you here. We actually happen to have more than one L, so I just need two of these, so I need to include all of them. So let's just go here. Well, what's the KEQ expression? The KEQ expression is going to be products over reactants because none of these are pure liquids, none of them are solids. I'm going to have C6H5Br. It's going to multiply the HBr. We're actually going to do that math in the ice table stuff. We have C6H6 on the bottom, and then we have a Br2 on the bottom. Right? That's it. That's our KEQ expression. How about the other one here? So we have, this time this is the only L in the entire expression. This time we have to ignore it. So therefore we're going to have KEQ. Sometimes they try to change this notation on you. Sometimes they call this one here just K. Sometimes they'll call it KC because we're using concentrations. Pretty much it's just an equilibrium constant. Our product in this case here, I'm going to ignore it. So I'm just going to put a 1 over. The bottom here, this is gas, the other one is gas. It's a little bit weird to see that half there, but so be it. Remember the numbers in the balance equation just go up into the powers. You might see that in your answer keys written as square root of oxygen because to the power half actually means root. Alright, so that's your KEQ expression. What if I told you I was at a certain temperature that the KEQ was 50, right? What would that mean, right? If I gave you that, KEQ was this ratio, products or reactants. As long as this fraction is bigger than 1, this means products are favored. This means even though we are most definitely at equilibrium, forward rate is matched to reverse rate here, there's no sort of imbalance in the formula, but when I actually look at the numerical values here, in my system, I have way more of the H2O and only the odd H2 and O2. That's what this number here represents for me. And then again, we use the terminology products are favored. Okay. So with that, it's a little bit of preface here. Let's take a look at an ice table. Okay. So let's just do this by way of an example here. Let's start off with an equilibrium. So PCl5 as a gas. It's an equilibrium with PCl3 as a gas and Cl2 as a gas. All right. Again, just conventionally here, we would read our reactants are on the left side and our products are on the right-hand side. Right? So this question here is worded at equilibrium. I'm going to say EQM for short. At equilibrium, there is 3 moles of PCl5, 4 moles of PCl3, and 5 moles of Cl2. I'm going to tell you this is within a 2-liter bulb. Bulb is just a fancy name for a container. Okay, so the size of the room is 2 liters. What I want here is I want us to calculate KEQ. Don't just give me the expression like we just practiced here, but since I gave you numbers, actually tell me at this specific temperature, they didn't mention what it was, but at this temperature, what is my constants value? So I would always start off with a KEQ expression if we can. So KEQ is supposed to be products over reactants. Our products this time are PCl3, Cl2, those are gases, so we include them, divided by PCl5. So what this says here is, for us to find the KEQ, I would just need to know the concentrations at equilibrium. As I read this problem, I'm already told these are the amounts at equilibrium. So we've already hit this equilibrium, there's no more changes in concentration, those concentrations are now constant in time. All this involves here is, because we are at equilibrium, I can just find the concentrations. So let's find, for example, what is the PCl3 at equilibrium? Well, I have a 3 moles. I happen to be filling in a 2-liter container. Well, that's 1.5 molar. What's the PCl3? Sorry, I meant PCl5 for the first one. What's the PCl3? The PCl3 was 4 moles. So someone has gone in with a meter here, and they've actually calculated how much of each amount they have. Although the ice table would work with moles, we're going to see an advantage doing concentration. So 4 divided by 2 here. So that concentration is 2 molar. We also are given the Cl2. We're given all the information. So 5 moles, that's also in a 2-liter container, so that's 2.5 molar. Since I know the concentrations and we're guaranteed we're at equilibrium, we can just plug this into the problem. We can say that the PCl3, well, that's 2 molar. And then we have our Cl2, well, that's 2.5 molar. Divided by PCl5, which are 1.5. This is just going to give us a numerical value. 2 times 2.5 divided by 1.5. This is giving us, to our sig face here, 3.3. What does that number mean? Again, this number here is KEQ bigger than 1. That means products are favored. That means we have a situation where at a temperature where we have more of the PCl3 side than the PCl5 side. Right? Easy as that. This is now a constant for us. What if, part B of the question, what if I have another situation? So let's say part A, part B. What if, or what is, let's do what is the new moles of CO2 if another equilibrium, so different from earlier, if another equilibrium has PCl5, let's change that to 4 molar, and PCl3 is, earlier was 2 molar, so let's make it 6 molar. Okay? So between A and B, you'll notice, actually I should emphasize here, this is, oh, it's equilibrium, yep, okay. So what I want to emphasize here is between A and B, there was no mention that temperature has changed. You didn't see me sneakily go, oh, that was at a starting temperature and suddenly this is a new temperature, because there's no implication that temperature is different. We can actually make use of this 3.3. This 3.3 will now always give me the relationship between PCl3, Cl2, and PCl5, right? So now it's just a little bit of math then. If I just rewrite that expression here, KEQ was the PCl3, Cl2 divided by the PCl5. I'm going to take the same constant because I was told this is the number we had assumed the same temperature, right? That's 3.3 here, and let's just plug and play here. So if the new PCl5 at this new equilibrium happens to be 4, so the bottom number here is 4.0, the PCl3 is 6 molar, that's going to be 6. You see that we actually have all the numbers, and we can find the Cl2. Note this only gives us concentration. Anytime you need to find moles, well, I'm still in a container that is 2 liters big. I can do that as a last step. So let's find here how much CO2 that I have. Take the 3.3. If it's unrounded, even better. So 3.3 times 4 divided by 6. The concentration in my new system is actually 2.2 molar. And remember my bulb, my container happened to be a 2-liter container. For my concentration to be 2.2 molar, we can just go, if you need to, you can go C is equal to N over V. So therefore, N is just C times V. Take the volume times the concentration. So what is the moles of the CO2? That's what they're asking in this problem here. Take your concentration, which is 2.2 molar, times it by 2 liters. And this gives us here 4.4 moles. All right? So there we go. We started seeing a little bit of the math here. If I'm given a lot of information, first emphasis here is it has to be at equilibrium, because these values here have to be at equilibrium. But if I know all those numbers, I can find this ratio. I can get this constant. And then assuming that the temperature is unchanged, this 3.3 stays true, you can then tweak the PCl3. You can shift the equilibrium all you want, and you can always look for the unknown. All right? So that's our first setup here. Somewhat easier of a setup. Next problem here, I want you to compare the problem that we just did to this next problem. I want you to just sort of read this problem to yourself here and tell me what's different about this way of framing it. So I have PCl5 in equilibrium with PCl3 and CO2. Exactly the same ordering, exactly the same everything. This is gas, gas, and gas. I'm going to word this problem here. 5 moles of PCl5 is initially placed into a 2-liter bulb, just because we have some familiar with that 2 liter. It could be 1 liter as well, but I have a 2-liter container at equilibrium. Once it hits this sort of balance point, at equilibrium, there is 1 mole of PCl3 present. I want you to calculate KEQ. Okay? So I borrowed the same equation here. It's exactly the same. Reactants becoming products. Even the expression is the same. What we're interested in is still calculating KEQ, like that first problem that we just did. So let's start off. Well, what I want KEQ, it's products over reactants. Oh, this is easy. PCl3 times CO2 divided by PCl5. But I want to remind you here, this constant here has to use the equilibrium values. We do have one value at equilibrium. At equilibrium, we know that there's 1 mole for the PCl3. But unlike earlier, I did not tell you what's the equilibrium for CO2, what's the equilibrium for PCl5. The other change that I've swapped on you here is, notice there's some sense of time passing. There's an initial. I started off with my container, it was a 2-liter bulb, and what I decided to do is I decided to pump in 5 moles of PCl5. That's all I put in. I didn't put in any PCl3, I didn't put in any CO2, I just started off with reactants. Are we at equilibrium at this point? Well, no, to be at equilibrium, we need to have both reactants and products present. I need the forward rate to equal reverse rate. So because there is a sense of time passing here, it's not so easy to actually go straight to a KEQ. So there's a little bit of sort of preliminary work we need to do before I can punch into this expression. Because there is an initial and there's an equilibrium later on, I'm going to set this up as an ice table. We'll know to do an ice table if there's this sense of time passing here. You're actually going to use the equation as a heading. So PCl5 is a reactant. This becomes here PCl3 and CO2. So that's my heading for my ice table. We're going to do ICE down the side. That's our ice table. The I stands for, what do we know at the beginning? The C stands for a change line, and the E stands for an equilibrium line. This is what we know once we've actually hit equilibrium. So now I have the sense of time passing here. I can sort of track down in this table where my numbers, what information I'm given. So initially, I placed 5 moles into 2 liters. So we can do this concentration here. Concentration of PCl5, I'll even put an I here for initial, is 5 moles divided by 2 liters. That's always something you want to do first, especially if your volume is not 1. Make sure you find the concentration. I pumped in enough particles of PCl5 so that the concentration in my 2-liter bulb is 2.5. But again, this is an initial. So for the PCl5, I decided to pump in 2.5. Right? It's implied that it's going to be molar, but I'm just going to emphasize that for now. Notice they didn't need to say, oh, by the way, I didn't add in any PCl3, CO2. Just the wording of the question, that's what it seems like, right? I have this bulb, I pump in PCl5, not pumping in anything else. So what you can do is you can actually add in, well, I had none of the products to start off with. At equilibrium, I'm also given a number. At equilibrium, I have, for the PCl3, totally different chemical, but this is at equilibrium, I'll put an E there. At equilibrium, it's 1 mole worth of this chemical, also in a 2-liter bulb. At equilibrium, my concentration is actually 0.5 molar. So look down the column for PCl3, not for the initial, I didn't put any initially in, but at the end, it's actually 0.5 molar. So as time passed, I progressed from having no PCl3. As we were approaching equilibrium, we had actually gained a little bit here. I actually know what the PCl3 is. What's nice about this equilibrium here is this change line in particular, the change line, because the change line is during the reaction, the change line has to follow the mole ratio. Change line follows the mole ratio. So while your starting amounts don't have to follow the mole ratio, the mole ratio was a 1 to 1 to 1. Just because you put in 2.5 PCl5 doesn't mean necessarily you need to put in 2.5 PCl3, 2.5 CO2. I notice I put in none of that. But over the course of the reaction, as the PCl5 transforms itself to become PCl3 and CO2, for every 1 PCl5 that I lose, I'm going to get an equal part PCl3 and equal part CO2. I'm going to see that on the change line here. And what we're going to do here is we're going to say, well, I started off with no PCl3. I know at the end of the day I have 0.5, so this one here had to have gone up by 0.5. This not only has found for me here what one of the change line values were, it actually decides which side is actually going to be a plus. If I plus on the product side, CO2 is also a product. This one here also has to be a plus. The other side has to be a minus. One side has to gain, the other side has to lose, because we're stuck in the same equilibrium. Now using that simplification here, because the change line follows the mole ratio, if the PCl5 has gained by 0.5, it's in a 1-to-1 ratio with the CO2 would similarly have gained by 0.5. How much has the PCl5 lost by? Well, again, 1-to-1 ratio, it's lost by 0.5. Now, by tracking down those changes here, I can figure out at equilibrium, I had 2.5, I lose 0.5, so now I'm down to 2 molar. I had no CO2 to begin with, and now I have 0.5, and now notice I actually have, through my ICE table, I found the equilibrium concentrations. That's like the earlier question, oh, by the way, these ones here are all the equilibrium concentrations, can you plug them into the KEQ expression? It took a little bit of work to actually get to those numbers, but once you have that line there, this is a nice little hint for you. Whenever you have the values on the E row, you can just sub them directly into the KEQ expression. So let's just try it out here. I would still write out the expression with the constants in there. PCl5 is 0.5. The CO2 is also 0.5 divided by PCl5, which is 2. This is just going to give you some number. The size of this number represents at equilibrium, which side is actually favored. So our constant is 0.125. Looking at our sig figs, we're putting numbers with like two decimal places going, two sig figs going into it. Let's just convert that to 0.13. And again, what's the implication of that? This one here, the KEQ is less than 1. So that means we have a situation where reactants are favored. Is that true in our ICE table? Well, even though we're at equilibrium, even though these concentrations are going to stay steady in time, the PCl5 is constantly going to become PCl3 and CO2, as the PCl3 and CO2 are going to constantly become PCl5. At this equilibrium, it looks like we have way more PCl5. So all that is consistent. Right? So that's how we do with it here. I want to make one other note here. Notice KEQ is just a ratio. It in general talks about concentration over concentration. KEQ is always something that has no units. Now, if you look really in particular here, well, this one here is molar, this one here is molar. Shouldn't I still have molar left over? There's a little bit of background for this, why the molars cancel out. But basically for us, just treat the KEQ as actually having no units. We can say in the math here, it's dimensionless. Okay. It's just a number. The size of the number represents how much I have. Right? I'm going to give you one other, just a sample ICE table here, slightly harder setup. So let's look at another equation here. We have H2 as a gas, I2 as a gas in equilibrium with 2HI. I know all of these are in equilibrium. I could have written 2HI and then H2 and I2 on the other side. But again, by convention, I still say reactants on the left, products on the right. This time, they're actually going to give you the KEQ value. I'm going to give you the KEQ value is 62, right? So already just purely from the number, you can say we're at a temperature where products are favored. We have a lot more products than reactants. That's what the size of that number tells you. So let's read through the wording of this question here. When 0.200 molar H2 is added to 0.200 molar I2, you notice I helped you out a little bit here. I'm not talking moles and the size of the container anymore. I've already given you the concentrations. They've already worked out that division. I'm going to put that into a container. When that is added to this and allowed to reach equilibrium, we just give it the time that it needs to settle out, to get the forward rate matching the reverse rate. I want you to calculate or calculate the equilibrium concentration. How much is left at the end of it? Equilibrium concentration of HI. Okay. So that's the problem set up. It will involve an ice table. How do we know it needs an ice table here is there some sense of time passing? So in this case here, we see that there's a start. At the beginning, we had a container of a certain size. You had put in 0.200 molar H2, and you put in 0.200 molar I2. I put in just the reactants. There was no mention of me putting in any products. So in that case there, I know I can't be at equilibrium yet. It's given a little bit of time. It's allowed to reach equilibrium. And once it reaches equilibrium, I want to know the equilibrium concentration. So again, let's just set up our ice table. If there's any sense of time passing here, we're going to go H2 and I2 is in equilibrium with 2HI. Make sure your equations are balanced. We're going to have our ICE down the side. So this is ice table. Initially, our H2 that we put in is 0.200. We put in 0.200 of the iodine as well. This time, I don't know any numbers. Earlier, I was given one of the numbers. That way, I can track the change line, and then I can work out the mole ratio. This time, instead, I'm given what the constant is. I'm given this number, but I'm not given any other information. So let's see how this ends up working out here. Again, just sort of curiously here, because I told you I added hydrogen, I added iodine, there's no implication I added any HI. You can come along and you can add a 0 yourself, right? Because there's no implication that you actually put that in. We need to decide which of these sides is going to be a plus and which of these sides is going to be a minus. It's a little bit easier this time because I can't drop any lower than a 0. So if we are supposed to come to equilibrium and I'm supposed to have some products, I know this side has to be a plus, the other side has to be a minus, no matter what you do. What we do in math class is when we don't know what the variable is, I don't know what the change is, I'm going to use an x. Let's say the hydrogen drops by x. Because the iodine is in a 1-to-1 ratio, the iodine also drops by x. The only one that's different is HI actually is going to climb by 2x, so plus 2x. Normally what I tell people is if you know the I and the C row, just crunch through that math there and tell me what the E is going to be. What's 0 plus 2x? Well, 0 plus 2x is just 2x. What's 0.2 minus x? Well, I have no clue what it is, but I can still write it. If you told me what x is later on, it's just 0.2 minus x, 0.2 minus x. So, doesn't seem to be very helpful here, but at least I filled in the table with these placeholders. Again, what we're going to do, whenever you have these numbers here in the equilibrium row, you're ready to put it into the KEQ expression. KEQ is a product over reactant ratio. I would still write out the expression. My products this time are HI, square it, all over H2 and I2. I'm just going to punch those numbers directly in. Notice that we actually have the number. KEQ is actually 62. Not a super nice number, but we're at a temperature where the constant is 62. My placeholder for the HI at equilibrium, you're only going to punch in the equilibrium row for the time being. So you're going to punch in 2x all squared divided by, on the bottom, they kept the numbers fairly simple, 0.200 minus x, 0.200 minus x, and in fact, this is actually going to be 2x all squared and then 0.200 minus x all squared. Now, if you worked out the math at this point here, you would end up with some terms that are squares because you're foiling and you're actually multiplying in. You're going to get a power 1 term. This would end up in a quadratic. However, they always work the numbers really nicely for you. So this is a nice simplification for us. In Chem 12, we won't, or we don't, need to use a quadratic, the quadratic equation. So they're going to work out the numbers so nicely. This time they worked out nicely because the H2 and the I2 were pumped in with the same numbers. In this case here, because both of them are being squared, what we can do mathematically is we can actually just take square roots of both sides. Now I know the square root of 62 is not a nice number, but it's just going to give you some decimal. Root of 62 is 7.87, give or take. When I take a square root of two things that are multiplied, it basically gets rid of both of the squares for me, and therefore I'm left with 2x over 0.200 minus x. So I still have no clue what x is. At least this looks a lot more simple. Now let's just crunch our way through the math. I'm going to bring this binomial up because I want to pull the x term out. This is equal to 2x. I'm going to distribute the 7.87 in, times it by 0.2. So this gives me 1.57 minus 7.87x equals to 2x. Collect up like terms, add up the 7.87. So 9.87x is supposed to be 1.57, and therefore x is 1.57 divided by 9.87. Give or take a little bit of rounding, I'm getting 0.16. Right? It may very well be a lot of work for you. Wow, we have to do an ICE table. We need to solve through a lot of algebra to actually get to this x here. Always do yourself a favor. When you find out what x is, go back and reread the question. What were they after? They may not have been after what x is. When I reread the question, they were asking for what is the equilibrium concentration for the HI. So I look at my ICE table here. They're looking for the equilibrium of HI. They're actually looking for 2x. So therefore, like this problem here would probably be out of 4. And if you just solve the algebra, you would get 3 out of 4. If you're missing this last step here, they were actually after the concentration of HI at equilibrium on our ICE table was actually given by 2x. They actually want you to take 2 times this 0.16, give or take a little bit of rounding. So there we go. I started off with no HI to begin with. I knew I had to gain on the right-hand side, and I now know that the concentration is 0.32. If you like, you could also calculate what's the concentration of H2 at equilibrium and I2 at equilibrium. They kept those numbers the same. Well, our expression had said 0.2 minus x. Now I happen to know what x is, 0.200 minus x, 0.16. And therefore, we are at equilibrium, making sure products are favored. In this case here, our reactant amounts here are just 0.04. And we see from the numbers here, we would actually have 0.32 of your products. We will only have 0.04 of these reactants after you do the minus, and that explains the fact why your KEQ heavily favors products. All right. So just introducing to you ICE table here. We'll do another small twist of this in tomorrow's lesson, but just play around with some of the calculations and we'll see how we do. Thanks, guys.